All right, it is 3:10 by my clock.
Yes, and I'll do a quick introduction and then get you going.
All right, excellent.
All right, so good afternoon, everybody. Welcome back after Thanksgiving. Today's talk is on data and related issues in applying machine learning to cybersecurity by James Halvorsen from Washington State University. And he is a PhD student in computer science at WSU. His research focuses on cross sections between machine learning and cybersecurity, emphasizing generative machine learning techniques and intrusion detection systems. So I'll turn it over to James. And before I turn it over to James, there will be a survey at the end that we'll do just to help us with our evaluation. So we appreciate it's just a couple questions if you can fill that out. So go ahead, James.
All right, thank you. So, a while back, I did a presentation on machine learning applications to cybersecurity, right? Some of you might have caught on that. Others might have missed that. I'm not so sure. But I'd like to begin this presentation with a brief recap of that because that kind of puts into context why I'm researching this topic of data in specific and trying to create data sets and whatnot. Um, and so, what is machine learning first and foremost? Well, we could describe it as a set of tools and techniques that, given some data set, we want to learn a function of some sort or otherwise discover some sort of knowledge. And that function is usually um, grouped into something like classification, where we try and determine what of several groups that data belongs to. Like, for instance, we might have a bunch of pictures of road signs, and we want to determine if this is like a stop sign or a 45-mile-an-hour sign or whatnot. Or regression, where we're trying to learn um, some pure mathematical function and whatnot. Um, and we have several different types in which each of these algorithms we have for learning can be categorized into, right? So there is supervised machine learning, and this requires that data has labels, right? So if you want to predict that, um, this sign or this image corresponds to this sign, you have to have a mapping already of each of those images and each of those labels. Otherwise, it can't predict what that's supposed to be. Unsupervised machine learning, by contrast, has no labels, and instead, you are trying to find a way to separate that into a bunch of different categories. Your input here is going to be, say, um, divide this into 3 groups, cluster it. And then beyond those two, there's also reinforcement learning, where rather than trying to purely classify like what type of group something belongs to, you might say, well, we want to learn some sort of policy that's going to decide what actions we're going to take. Reinforcement learning tends to be used for like an AI to determine actions and whatnot. And we've got several different algorithms for making these different machine learning models, ranging from decision trees, which are rather simple. It's like a giant if-else chain, to support vector machines, and neural networks, which are several different layers of matrix multiplication chained together, along with some activation functions. So where is this used in cybersecurity? Well, the most researched topic on this is intrusion detection. So we have a bunch of data that we're collecting on our network of machines, and we want to use that to determine whether or not there is someone attacking us, right? If someone tries to launch a cyber attack, we would like to be able to raise an alarm, or if we have an intrusion prevention system, which is a sort of extension onto the intrusion detection system framework, we would like to also respond to that threat and lock them out. These have different a lot of different implementation types. So there's host-based, which are focused on like preventing intrusion on a specific machine, and network-based, which tends to monitor the network traffic and tries to prevent hosts from getting further within a network. And there's also signature versus anomaly-based. So signature would be kind of like your virus scanner in a way, where it has a bunch of signatures of what an attack looks like already, and if it finds the attacker's behavior is inside of that list of signatures, we can raise an alarm. Otherwise, if they are doing something new, we actually can't raise an alarm. So that's a weakness of a signature-based intrusion detection system. And anomaly-based are more trying to say, does this behavior that we're watching differ significantly from how we normally observe behavior on our network? Which that type of intrusion detection system has a huge issue with false positive rates. So when you're trying to evaluate whether an intrusion detection system or intrusion prevention system is effective, you're probably going to be wanting to detect things not just in terms of true positive rate, where we're saying, like, do we catch the attacker often enough, but also false positive rate in specific, because if we have an attacker that is, or if we're catching too many people as attackers when it's actually just benign traffic on the machines, then the IDS is going to be turned off, most likely. And then we aren't going to be catching anything. Other types of applications include incident response, where we're trying to find a way to appropriately respond to an attack that we've detected, which may require answering certain questions about the attacker, like what goal do they have, right? Like, are they trying to reach like a certain machine and extract data from it? Can we shut them out from access to that machine? Or do they have some other goal that we need to stop? Finally, we have automated red teaming, where we are trying to use like an AI in order to attack a network and find weaknesses in it. And I've discussed before on this an existing work that uses reinforcement learning in simulated environments to be able to conduct this, right? But most of what I'm going to talk about today is going to be intrusion detection. So, data. Why is this something I'm researching and talking about today? Well, let's put ourselves into the shoes today of a computer science PhD student. Actually, that would be me several years ago, specifically. And this PhD student wants to research intrusion detection, right? Because the idea is a bit appealing. If we can automate a way how to respond to cyber attacks, we can prevent a lot of cyber attacks. So if we want to implement this, what do we need? Well, first and foremost, we need a test bed, right? Something we can conduct experiments on. It's possibly going to be some hardware, might be some virtual machines. And secondly, if we want to implement anything with machine learning, we need a data set. So let's look for some data. Well, the first thing is, like, what would be an interesting topic to find or to do security on, right? Say I want to research power grid security. I would need to find a power grid security data set, right? do we have any data sets where we have people attacking power grids? Because we know that it's happened in real life before. Surely they would record that data. Well, no, because that kind of data is extremely sensitive, and we don't have that kind of data being created synthetically because it's kind of a pain to set up. Not many people have the existing knowledge of how to work with power systems and also work with cyber attacks. So I don't find that particular data set. But oh well, let's look for network security data sets. And lo and behold, I do find some. But the quality of these is not that great. One that I'm finding that is really commonly used is KDD99, which is also really old because it's from 1999. Then I find some data sets that are more modern, but they could be described as single class data sets. So this has a bunch of network traffic that we've collected, but we don't have any attack data in there. So it's not particularly useful. I would have to find some way of injecting cyber attack data into there. Others I find are unlabeled. So we've conducted several attacks on our test bed, and we've recorded all of the traffic going on in that test bed, but we never bothered to label it. In one case, I found a data set where there was a ground truth report that discussed all of the attacks that happened and what time they occurred, but this was never labeled inside the data set, which was over a terabyte in size. So it would be extremely laborious for me to label that myself. And then after those, I find some data sets that actually do contain labeled data, but they are unbalanced. So we say we have, 99.5% is benign traffic, and 0.5% of that is various attacks that we've conducted. If we train a machine learning classifier on that, right, predicting an attack is sort of a margin of error there. If we just predicted everything as benign, then we would have 99.5% accuracy, which is pretty good. We'd have a very bad false negative rate, though. So what am I seeing in all of the existing IDS research, though? Well, a lot of people make their own data set and then they don't share it. So they'll work on their own test bed and they will conduct attacks within that test bed, and then they'll train IDSs on that data and they'll report on that, but they will not share the data that they collected to be able to train that. So we have no reuse. Okay, so let's do that ourselves. Say we decide to set up a test bed, but then do we actually have the budget for hardware to run this many machines, or are we going to have to run virtual machines? Then let's go conduct some attacks. But which attacks do we conduct? Do we conduct denial of service? Do we conduct some buffer overflow attacks against some vulnerable software? Which vulnerable software do we collect, etc.? It's kind of a difficult question of how to conduct a bunch of fake cyber attacks. We also might want to have someone who's a bit more experienced with this, someone who does pen testing for a living, but that would be expensive. So can we try using some tools for generating these? And these are called adversary emulation, but that may still require some advanced knowledge of how to work with these. And all of this is going to take time, because not only do we have to conduct all of these attacks, we also have to label all of that data, which brings us back to the same problem we had when we were dealing with the unlabeled data sets. And then there's another question. What types of data are we supposed to collect in the first place? Because, as it turns out, there's a lot of different types of data when working with cybersecurity. Within network data, we are concerned with both net flows and PCAPs. So net flows are sort of a summary of network transactions. They'll tell you things like the IP address, the ports, how many bytes were sent, how many packets were sent, etc. But they'll not really go in depth beyond that. And a PCAP will tell you, okay, we have a log of every packet that was captured, and we can tell you every single byte of that packet. So if you wanted to, say, log all of the HTTP packets, you could know all of the fields in that HTTP packet. With host data, we have security logs, like different alerts that we've had from existing security tools on the operating system. And then we have a bunch of different event logs. We can log whenever a process was created or a process terminates, a file's created, a file's modified or is deleted, whenever a driver is loaded. Basically anything anytime happens on an operating system, we could log that. So we have a ton of different data we could collect. So how much do we collect? If we do everything, then we have a needle in the haystack problem. We could have something happen on here, and we would definitely have evidence of it, but we also would not be able to find it happening. And if we don't record anything, then we have no records of the attacks. So somewhere in the middle is the answer to our question, right? And so that leads to a metric for how do we determine relevance of data. So suppose we have a network of computers, and we want to know on each computer, what data do we collect so that we will have the maximal ability to show attacks that we would receive, but also we don't want our normal behavior on this machine to be incorrectly predicted as an attack, right? We don't have a lot of false positives caused by collecting everything and then having a bunch of noise around here. And currently, the solution is a tool I've worked on a few years ago called Tomato. And that uses some conditional probabilities and Markov analysis to try and figure out where is the most likely machines to be attacked if we were to simulate a bunch of random attacks. And also on those machines, if we look at all of the traffic that we normally get, right? What of that would most likely be predicted wrongly as an attack if we were to, say, apply some objective rule set? Which for that we use the MITRE attack framework and then just looked at whether or not the symptoms of various attack tactics could be found within the benign data here. This metric, I think, could be improved upon, particularly because it's difficult to answer that question of how do we determine whether or not normal behavior would be seen as an attack. But That's just one problem. Okay. What if instead of trying to create our own data sets, we just focus on taking the existing data sets and making them better? And for that, we're going to turn to generative machine learning. We have a number of different tools, which I'm going to go over here. Generative adversarial networks, variational autoencoders, and diffusion models are some of the more popular methods of generating data that I've found. And I have found quite a bit of research that shows that when it comes to the balance problem, at least, where we have too many of one type of class and not enough of another type of class, that generative models are very good at solving this problem. That said, with data, with security data, there are certain issues that can come up that generative models are not as good at producing security data. But let's talk about those generative tools for a moment. The first of these tools I'd like to talk about are generative adversarial networks. They are probably the most well-researched method in terms of number of papers I'll find on Google Scholar. And they're also some of the easiest to explain because they just have two neural networks, what we'll call a generator and a discriminator, and they train each other through an adversarial method. So the generator is training by optimizing how badly the discriminator performs. If it can cause the discriminator to misclassify, then that is an improved generator. This process has been compared to counterfeiters and police as the most common analogy. So the generator is like a counterfeiter. It's trying to produce counterfeit images, and the discriminator is like the police trying to be able to determine if things are counterfeit. And this ends up producing a lot of high quality data, but also they're a bit of a pain to actually train because of an issue called mode collapse, which is where, they will accidentally end up producing the same images every time. So the generator finds a couple of images that it knows that the discriminator knows are real because the discriminator is receiving input from both the generator and a bunch of real data samples. So if it ends up discovering a real data sample, it can just produce that data every time, no matter what random input you provide to the generator, and it will just produce that data. So the solution to that right now is a loss function called the Wasserstein loss function. So that is so common, it's now a variant of the GAN called the Wasserstein GAN. There are many other different variants, including bidirectional GANs, which, in addition to training a generator and discriminator, also create an encoder that can take the generated image and then reproduce the noise that was inputted into the generator to produce it. Additionally, there are conditional GANs, which allow you to, allow you to add some additional conditional function in there so that you're not just producing, say, something from one data set. You could say, I want you to produce something from this data set with this label, or some other specific feature. And there are also deep convolutional GANs, which are just using deep convolutional neural networks, and several more. The next type of generative model I'd like to discuss are variational autoencoders, which are a method of training a model called an autoencoder. So there's actually a lot of research prior to this on developing autoencoder models, but this is using a different method of training that uses Bayesian inference. But the autoencoder as the end result always works the same, where we have two neural networks, the encoder, which will take something from a real data set and turn that into a latent representation, and a decoder, which can take that latent representation and then return the original data from the data set. And if you are to take some random noise and put that into the decoder, then it works exactly the same as the generator from a GAN, where it will produce something that should look similar to something from the original data set. Variational autoencoders are about as old as GANs, but when they're used for image generation, the results are often a little bit blurrier. Although I can't really say as much about how they're used for other types of data in terms of quality because of some other issues I will go over soon. One variant on this is conditional variational autoencoders, which can be used to generate structured data, which is, instead of just generating a feature vector, it could be a more abstract structure like a matrix or something like that. And then there's diffusion models. These are relatively new, at least with regards to their ability for generating data. And they use a denoising process to learn to generate data. So if you look at this figure over here on the left, right, we have some of these images where from the right to the left, it gets blurrier and blurrier. And that is because they are adding noise progressively. And then they're learning to reverse that process so that you can get the original image. And thus far, these diffusion models have had a lot of success in image generation. You may have heard of various AI art programs like DALL-E 2 or Stable Diffusion, and this is the basis for those tools. I have not seen as much work on them being used in cybersecurity. However, I think that they will be dominating it in the next few years. Okay, I mentioned some issues on cybersecurity data being used with generative models. What are those? The first is feature extraction, because all machine learning models, whether they're generative or classifiers, like to work with feature vectors, which are constant width arrays of IEEE floating point numbers. And when we have an error in, say, generating that data, we want that error to actually correlate in a way that is dealing with the magnitude of that error. So if we are off by 1 in some floating point value we're generating, that should be a lot less worse than being off by, say, 200. But many security features don't map over that way. So let's say we're dealing with something like a port. If we were to just directly take the integer value and turn that into a floating point number, because of course, the range 0 to 65,536 does fully fit within the IEEE floating point numbers. Is there a difference between getting port 23 as port 22 or port 23 as port 223? Well, they're both wrong. They're completely different. So they're equally bad, but we shouldn't have that. We should be able to get closer and closer and be a better answer to this. So what are some techniques we can use for this? One of these is called one-hot encoding. So for every possible value in that category, we will have a single floating point value that's either 0 or 1, right? And if we have 65,536 ports, then we're going to have a very, very large feature vector because that's 64K floating point numbers just to represent one field. So that's not ideal. Then we have binary encoding. That's a little bit better. So we could take the 16-bit floating point value, or we could take the 16-bit integer and say each one of those bits is one floating point value. So we've got 16 floats to represent one port. And so we can still kind of get that off by one is equal. Everything could be equally off by one. If you're off by like this is very hard to describe, but you don't have the off by one error as hard with binary encoding. And also, we want to try dimensionality reduction in general. So if we can find a way to use less bits to encode, like say an IP address is 32 bits, but if we only find we have certain /8s there, then we might be able to reduce ourselves down to, say, 12 bits, and we have even less errors to concern ourselves with. Going even further with feature extraction, let's look at some of the features that we've got for each of our different types of data. NetFlow has to be concerned with IP addresses and ports, as I've just described, but it also has integer features. And these can be more easily ported over because the off by one error is not as much of a problem. But then we have to go into some of the host type issues like security event logs. Text fields can be purely categorical, like event types, so we could figure out, okay, we're going to figure out every possible event type, and then we're going to encode them into like a one-hot encoding or into a binary encoding and call it a day. But then we run into an issue if one of those fields is like a file path, because even if we consider all possible file paths on one system, what happens when we try and train, or what happens when we try and take this model and then put it into an area where it's going to encounter a file path that wasn't in the training data? Well, that's going to be a problem, because then how can we represent that for it to be able to classify it correctly? And for other types of intrusion detection, there's malware detection, and we can't really encode instructions as easily into feature vectors. So instead, what we'll use are function call graphs or system call graphs and whatnot. And we'll just say what functions were called, not necessarily talking about what order, but perhaps what quantity. Additionally, there isn't as much work on trying to generate malware data using machine learning. Instead, I've found that a lot of the research is just using honeypots to capture them, which has some degree of success. Another issue with security data is trying to evaluate it, because when we're dealing with generated data, most of the research is concerned with images. And with an image, you can visually tell when something is wrong. In addition, since images tend to already use continuous features, a lot of the metrics that are used for machine learning already work pretty nicely because it's a matter of how far off are we on these red, green, blue values, which are continuous. But for a security data set, to evaluate it visually, right, you would have to, say, open up this thing in Excel and try and manually go one by one. Does this make sense to me? You could do this if you have a ton of time, but nobody has a ton of time. So we want a metric we can automatically do this with, and it should be able to evaluate realism in a way. So what are these metrics? Well, one is to use an IDS as the evaluating tool. We train an IDS on synthetic data and then test it on real data. And if it's able to predict the real data very nicely, then, well, you kind of accomplished your entire point of generating the synthetic data. So it makes it an easy type of metric. But also, we need some sort of point of comparison, like training on real and testing on real to compare to. Next, we have distance metrics. So we are trying to compare two different distributions, and we've got a handful of those. One of them is called the Fréchette inception distance. That is commonly used for generating or for comparing images generated by GANs. But one thing to keep in mind is that we are not necessarily comparing two data sets of equal sizes. So if we're trying to compare certain statistical differences between them, these metrics may have issues because we're trying to take something like 0.5% of the data set being attack data and turning it into, say, 20%. So they are definitely going to be different from each other in that respect. Finally, we can have metrics that are tailored to the data set. So if we know that certain types of states are invalid, we can create a custom metric that says, if we find any of these types of states, give it less points, otherwise give it more, for creating something that's realistic. Like, for instance, we're going to rate things lower if we find a port value that is greater than 65,536, or something like that. Other issues to be concerned about are data anonymity. So when you're capturing data in a test bed for creating the original data set, we may end up finding some sort of sensitive information that may need to be anonymized in some way. And if we are using a generator, we need to make sure that that is not going to be propagated into the new synthetic data. All right, summary. We know that machine learning has a number of applications in cybersecurity, but machine learning also is heavily dependent on data. We know that data sets for cybersecurity are often not very good or might not even exist on some domains. And we know that creating data for cybersecurity requires that we answer certain very difficult questions. So what types of data are even useful in this domain? That's the observability problem. How do we extract features that are useful for our machine learning models? And how do we evaluate the quality of our data? All right. Any questions?
So I don't see any questions in the chat. So if anybody wants to unmute and ask a question.
Hi, James. James Crab here. Hey,
All right.
along the lines of, the fact that in cybersecurity, a lot of the data is going to be unbalanced when you're looking at, some sort of illegitimate behavior versus legitimate use, just because, through the fact of that everyone uses, the internet and, you know, in regards to the total internet usage or networks or whatever, actually it's a very small amount of anything going on that's
Right.
an attack or fraud or something. In your work, how do you deal specifically with such unbalanced data sets, or do you just try to avoid them altogether somehow?
Well, the only data sets that you can find are unbalanced. So my work is trying to find ways to solve that balance problem by using synthetic generating tools, um, which has led me down to that rabbit hole of running into those difficult problems. So now I'm trying to say, okay, how do I solve those difficult problems so I can have better synthetic generation so that I can solve the unbalancing problem so that I can solve the intrusion detection problem.
Yeah, do you have like maybe a specific example of something that you've done with like what particular unbalanced data set you looked at some point?
One of those is the UNSW NetFlow dataset. Um, and that's about like 96% benign to 4% attack data. And so I've been trying to find ways of um, generating more malicious samples to improve this. And I've been exploring various techniques on trying to get GAN to train and produce better net flows for that particular data set.
Cool, thank you.
All right.
Okay, there's a question in the chat. Do you think more data sets will be made available open source to work in the future, or will it stay somewhat private as it is now?
I do think that over time there will be more data sets being created, but it's not necessarily going to be uh, created at a rate that is going to be, say, faster than it's currently been. So um, data sets become obsolete as the various attacks that were used to create them are no longer being used in the real world, which is why it's not exactly a good idea to use something like KDD 99. Um, and so there are always going to be people creating new data sets. But you're not going to have someone say, create a very good data set, and then we never have to worry about it again. We have to continuously be making more. And I think that because the process of creating these is so ridiculously expensive, especially in terms of labor, that synthetic tools should be used to pick up some of the slack. And as for whether I think the data sets people have been using in their own work could be made open source, I think there could be a cultural change possibly to get more researchers to open source the data sets that they've been using, because, I mean, at the very least, the tools for them to share them are out there. Stuff like CodeOcean allows you to share not only the source code for your programs, but also the data set itself. But because some of that may contain certain sensitive data, many of them might just not want to do it at all.
Okay, does anybody else, I don't see any hands up. Does anyone else want to ask a question? Thanks, Samantha, for your question. I will mention I put in the chat the survey, so if you all can fill that out, that helps us get feedback and as we work to improve the session, improve our seminar series. Also, I want to remind the undergraduates while you guys are thinking about questions. I want to remind the undergraduates to consider apply for the summer internship program at the Griffiths Institute. There's a link in the chat that you can get, but that really is an opportunity for you. And we do have some students that have done it in the past. If you have questions after you apply, but we really would like to encourage everyone to apply for that for this summer. Any other questions?
Another question, Noel. This is Asaf. I want to speak on behalf of James Crabb and have a little of an announcement to the grad students who have not responded to his request for meeting with mentees on projects and fill out the form that he has. So there are a few that are still on, I know, in this call. So please do that, and he will send an email to remind you tomorrow. And if you are an undergrad and you've met with your grad mentor, make sure that that's known to James as well. So look out for an email tomorrow.
All right, excellent.
Okay, well, so a bunch of announcements, but in addition to the survey, and so undergrads, make sure you apply for an intern. Grad students, make sure you respond to the email.
And thanks, James, for a great presentation. That was nice.
Yes.
Yeah.
Yeah, thank you, James, so much. And obviously, James part of the program. So if you have additional questions for him, we can definitely connect you with him. So we appreciate everybody being here today. I believe we have one more this in 2 weeks. We have one more webinar, so before the end of the year, and then we'll be working on the spring semester ones, or spring and summer, spring, winter and fall, winter and spring quarters, starting after the new year. So if you have any suggestions of people that you'd like to see give seminars, please feel free to reach out to us and we will start working on that. So thanks everybody for joining us. Bernie, did you have anything else?
No, I want to thank James for an excellent talk. Appreciate your preparation, and the method of delivery was really good. I will reiterate what Professor Schulz has said about the summer internships. There are 60 such internships for new students, and all students who've done internships last year have been pretty much guaranteed a second internship if they apply. So please do that right away. Decisions will be made in December, coming right up. Thank you.
All right. Thanks everybody for being here. And again, please let us know